All right, let's get right into it. We're living in this incredible age of AI, right? These systems can create breathtaking art, they can write code, they can even help diagnose diseases. But there's this really deep paradox at the heart of it all. Why do these super powerful, super smart systems sometimes fail in the most bizarre and honestly, sometimes dangerous ways? In this explainer, we're basically going to be detectives, trying to figure out why our smartest systems break.
And the stakes here are really, really high. This isn't just some academic problem. This quote, it's from a real-world situation where an AI was supposed to find pneumonia in X-rays. But instead of learning all the complex biology, it just learned to spot a little metal token that one hospital happened to put on its patients. So you can guess what happened. When they tried to use it at a new hospital that didn't use those tokens, it was completely useless.
And that really brings us to the core question of our whole investigation. How can a system that's smart enough to analyze a medical scan make such a simple rookie mistake? It's not just a glitch, it's a fundamental paradox, and we need to get to the bottom of it.
And trust me, this is not a one-off thing. Some research shows that over 80% of data science and AI projects just fail to hit their goals. This is a huge industry-wide challenge. So to solve it, we need to find the culprits. Let's start the investigation.
Okay, our first clue, this is the most common suspect you'll find at the scene of the crime. It's a phenomenon called shortcut learning. This is pretty much where the story of AI failure always begins.
So what exactly is shortcut learning? You know, you can think of the AI as a really lazy student who's just cramming for a test. Instead of actually learning the subject, it just looks for the easiest possible patterns to get the right answer on the practice questions. It's basically writing a simple if statement in its head, like, if background is green, then it's a horse, when it should be learning the complex function that actually identifies what a horse looks like.
And this example just illustrates the problem perfectly. I mean, if every single picture of a horse you show your model has green grass in the background, the AI might not learn what a horse is at all. It just learns that background equals green means the answer is horse. So you take that same model, drop it in Siberia with a snowy background, and it has no idea what it's looking at. It took a shortcut, and that shortcut just let it right off a cliff. This chart really shows you just how tempting those shortcuts are. See that little slice? That's the complex, correct solution we actually want the AI to learn. But just look at all the other options it has. It can overfit to the data, it can learn from totally useless noise, or as you can see from that big blue slice, it can just grab onto an easy shortcut. The path of least resistance is almost always the wrong one. But that makes you wonder, right? Why are models so drawn to these shortcuts? It can't just be laziness. To figure out the motive, we have to look deeper at the very nature of how these things are built. And that leads us to our second clue, the simplicity trap. Yeah, it turns out that the very algorithms we use to train neural networks, like gradient descent, have this built-in or inherent bias toward the simplest possible solution. You can picture it like a ball rolling down a hill. It's always going to follow the steepest, most direct path to the bottom. In the huge landscape of all possible solutions, the simplest answers are like the widest, easiest valleys for that ball to fall into.
Now, what's so interesting about this slide is how it shows you this bias in action. You've got two groups of dots, red and blue. The complicated orange line, that's the perfect boundary to separate them. But a neural network, it will almost always prefer the simple, straight green line, even if it gets a few wrong. Simplicity wins out over accuracy. And a really dangerous side effect of this bias is something called plasticity loss. Basically, once the network latches onto a simple answer, it can become totally rigid. It gets so confident in its little shortcut that it pretty much forgets how to learn, losing its ability to adapt when it sees new information. And this causes real physical damage inside the network. You get something called unit death, where neurons just get stuck on or off and completely stop learning. You can get parameter norm growth, where the model's internal numbers, its weights, get so huge that its predictions become super unstable. And then you have linearization, which is, well, it's especially sneaky.
Linearization creates what some researchers call zombie units. Now, these are neurons that are still technically active. They're not dead, but they've lost their superpower, which is their non-linearity. They've been reduced to doing simple math, like y equals mx plus b. They look like they're alive, but they're just shambling along, unable to do any real deep learning.
So far, these might sound like problems we can just engineer our way out of, right? But our third and final clue, it reveals something much deeper and honestly, a bit more troubling.
It's a fundamental law of mathematics that suggests a perfectly reliable AI might not just be hard to build, but in some cases might be literally impossible.
At the core of this whole paradox is this constant tug-of-war between accuracy and stability. You can build a model that's incredibly accurate on your training data, but it's often super fragile. Or you can build a stable, robust model, but you might have to give up some of that perfect accuracy. Getting both? Well, that's the holy grail. And it turns out it's mathematically way harder than we ever thought.
Let's look at the math for just a second. In a perfect, clean world, the relationship between an input, x, and an output, y, is simple. An AI just tries to learn the transformation, a, that maps one to the other. This equation right here, this is a perfect, clean signal. But of course, the real world isn't perfect. It's noisy, there are measurement errors, hidden factors, all sorts of chaos. We represent all that chaos with E, the error term. This little e corrupts the perfect signal, and that's what makes the AI's job so incredibly hard. It's trying to find the true signal AX, buried inside the noisy reality of AX plus E.
So, here's the crucial point, and this is pretty mind-bending. Research that builds on the work of giants like Gödel and Turing has found a shocking paradox. For certain problems, we can actually prove that a perfect AI model exists. But, and this is the wild part, there might be no possible algorithm that can actually find it using a finite amount of data. Imagine trying to predict the stock market. A perfect model might exist in theory, but the data is so noisy that any algorithm trying to learn from it might just hit a hard mathematical wall. It could get 99% of the way there, but be fundamentally barred from ever closing that final 1% gap because the true signal is just impossible to separate from the noise.
And this fundamental limit comes from the very building block of the whole system, the neuron. I know this equation looks complicated, but like the slide says, it's really just a simple process of weighing all its inputs and then deciding on an output. The paradox is that when you string millions of these simple little calculators together, you create a system so complex that its behavior can become fundamentally unpredictable and in some cases uncomputable.
So we've got our culprits: shortcut learning, simplicity bias, and the hard limits of math itself. The case might seem pretty grim, but this is where the investigation takes a turn. Because researchers have developed a whole playbook for fighting back, not by trying to achieve the impossible, but by building smarter, more resilient systems.
The guiding principle behind all these modern solutions is a really healthy dose of skepticism. For years, we worried about models being too complex, right? But now we know that solutions that seem too simple are just as dangerous. They're a dead giveaway that the model has found a shortcut.
And this right here is one of the cleverest strategies I've seen. It's called the too good to be true prior. It's a two-step move. First, you train a really simple, low-capacity network. Its whole job is to fail, specifically to find all the easy shortcuts in the data. Then, you use what it found to reweight your dataset, basically telling your final powerful network, hey, pay less attention to these examples, they're trick questions. It's like using a naive AI to vaccinate a powerful AI against making stupid mistakes. It's brilliant.
And that's just one tool in a rapidly growing toolkit. Let's run through a few others. First, layer normalization acts kind of like a governor inside the network, keeping the signals from flying off the rails and helping prevent that plasticity loss we talked about. Next is weight decay, also known as L2 regulation. If you're coding, this is like adding a small penalty term to your loss function that punishes the model for having weights that are too big. It forces the model to find solutions that are more stable. Then there's data augmentation, which is just creating tons of variations of your data, flipping images, changing colors. It makes it much harder for the AI to lock on to a lazy shortcut. And finally, adversarial training is like giving your model a sparring partner. You intentionally try to fool it with tricky examples to force it to become more robust.
Which really leaves us with this final big question. Our investigation has shown that AI failures aren't just bugs we can patch. They're fundamental properties of learning, of simplicity, and even of math itself. So if a perfect solution is sometimes provably out of reach, the challenge for us isn't just about building smarter AI. It's about designing systems with a deep understanding of their own limitations, and then deciding how and where we can actually place our trust in them.